Hello! This will be a demonstration of proposition 16 from book 6 of Euclid's Elements, which says that if four straight lines be proportional, the rectangle contained by the extremes is equal to the rectangle contained by the means, and the converse, if the rectangle contained by the extremes be equal to the rectangle contained by the means, the four straight lines are proportional. We're given, of course, four straight lines, A, B, C, D, E, and F. And we are either given that AB is to CD, just as E is to F, or we're given that the rectangle contained by AB and F is equal to the rectangle contained by CD and E. Now, in the first case, if we are given that AB is to CD, just as E is to F, we want to prove that the rectangle contained by AB and F, which are the extremes, is equal to the rectangle CD times E, which are the means. But if on the converse, we are given that the rectangle AB times F be equal to the rectangle CD times E, our task is to prove that AB is to CD just as E is to F. We're going to begin by constructing two straight lines, AG and CH, perpendicular to AB and CD respectively from the points A and C. We're going to do that by proposition 111, of course, because A is on AB and C is on CD, of course. And we're going to make AG equal to F, and we're going to make CH equal to E. And we're going to complete these parallelograms simply by proposition 131, just drawing these straight lines out like this. Right. So we're going to have that. So we're going to have the rectangle GB and, HD, not ED. Okay. Now, knowing that AB is to CD just as E is to F, and having made AG equal to F and CH equal to E, that was our first step, we can substitute them in the proportion to say that AB is to CD just as CH is to AG. But we notice with these two parallelograms, GB and HD, they are not only equiangular, right, because they have one angle equal to one angle, but the sides about these equal angles are reciprocally proportional. So AB is to CD just as CH is to AG. Again, the way you can identify reciprocal proportionality with these parallelograms is if you have two straight lines from the same parallelogram next to each other. Because normal proportionality would have AG to CH, but instead we have the inverse CH to AG. And that puts CD and CH, which are in the same parallelogram, next to each other. So that's how you can identify reciprocal proportionality. So we have the two parallelograms, GB and HD, which are equiangular and have the sides about the equal angles reciprocally proportional, which means by proposition 614 that equiangular parallelograms, which have the sides about equal angles reciprocally proportional, such parallelograms are equal, and so we can say that the parallelogram BG, or the rectangle BG, is equal to the rectangle CH. Now, AG having been made equal to F, the rectangle BG, which is ultimately just the rectangle AB times AG, is equal to the rectangle AB times F. We're just substituting AG for F here. We can do that by a property of magnitudes. So we can say that the rectangle BG is equal to the rectangle AB times F. And similarly, we can show that the rectangle DH is equal to the rectangle CD times E. Again, just substituting out this HC term. So by common notion 1, we can substitute the rectangle BG and the rectangle CH for their equals and say that the rectangle AB times F is equal to the rectangle CD times E. And this is what we set out to prove. Given that AB is to CD just as E is to F, we'd set out to prove that the rectangle AB times F is equal to the rectangle CD times E, which means we are done with the first case. Now to move on to the converse, we are on the other hand given that the rectangle AB times F is equal to the rectangle CD times E. Now we're going to keep the same construction, so just refer back to the first step if you forgot how to do that. So F is going to be equal to AG again, which means that the rectangle AB times F is going to be equal to the rectangle AB times GA. Again, substituting them out by a property of magnitude, so substituting one containing side out for its equal. We've seen this plenty of times since book 2. So the rectangle AB times F is equal to the rectangle AB times GA, which means that the rectangle AB times F is equal to the rectangle BG, right? Because the rectangle contained by AB and AG simply is the rectangle BG, of course. And now again, similarly, we can show that the rectangle CD times E is equal to the rectangle DH, right? Because E has been made equal to HC, which means that the rectangle CD times E is equal to the rectangle CD times HC, but the rectangle CD times HC is the rectangle DH, so the rectangle CD times E is equal to the rectangle DH. Which means that common notion 1, again having been given that the rectangle AB times F is equal to the rectangle CD times E, we can substitute these in for their equals to say that the rectangle BG is equal to the rectangle DH. But we have equal parallelograms, right? We've just shown that the rectangle BG is equal to the rectangle DH. And again, we know they're equiangular because they have one angle equal to one angle, which means, again, by proposition 614, that equal and equiangular parallelograms have the sides about the equal angles reciprocally proportional. We can say that AB is to CD just as CH is to AG. But again, we had made CH equal to E and AG equal to F, which means by a property of magnitudes, we can substitute them in and say that AB is to CD just as E is to F. Now, this being all that we set out to prove, we are actually done with the proposition, therefore, etc. Q, E, D. This is not so much an important prop for the rest of the elements. You'll see the next prop, 617, which is realistically just a special case of this, used a lot more. But this is a very important prop when you're doing algebraic geometry, because this is essentially proving the principle of cross multiplication, which you've probably seen, right? If you have two fractions, A over B be equal to C over D, you probably learned that you can do this weird technique of, I'm actually going to write it bigger. If you have two fractions, A over B equal to C over D, you probably learned that you can do this weird technique where if you cross multiply them, so if you take A times D and B times C, these products are actually going to be equal. So you're going to have that AD is equal to BC. Now, if you ever thought that was weird, I've always thought that's a little weird since I learned it in 5th grade, I believe is when I learned it. It's always just been super weird, and I never understood why that's the case. But with proposition 616, you understand that it has to be the case. Again, ratios being fractions, proportion being the same thing as equal ratios, and rectangles being the same as multiplication. Again, this is just going over stuff we saw in book 2. We can put this in terms of fractions and multiplication. So if you have two fractions equal to two fractions, then the rectangles, or the product of the extremes, which is just A and D in this case, is equal to the product of the means, which is B and C in this case. So given that A divided by B is equal to C divided by D, we can then say that A times D is equal to B times C. So yeah, you're going to see that a lot in algebraic geometry and just algebra period. So it's nice to understand why it's the case, and that's what proposition 616 provides. It substantiates the principle of cross multiplication. Having nothing more to say about this proposition, I will end the video here and move on to proposition 617.